Hey friends, today we'll learn about Kruskal's algorithm. We'll begin with understanding some of the basics of the graphs. In undirected graph, the edges do not point in any direction. But on the other hand, in directed graph, the edges point from one vertex to another. In connected graphs, there is always a path from one vertex to any other vertex. So in this case, if we have to travel to vertex number 2 from vertex number 0, you can either go with this path or you can go with this path. In weighted graph, every edge is assigned certain weight. A spanning tree is a subgraph of an undirected connected graph which includes all the vertices of the graphs with the minimum possible number of edges. So in this case, the original graph has 4 edges to connect 4 vertices, but we can connect these 4 vertices only using 3 edges. So that's why the spanning tree will look like this. For an undirected connected graph like this, there can be multiple spanning trees. These two are the examples of the spanning trees for this original graph. A minimum spanning tree is a spanning tree in which sum of the weights of the edges is as minimum as possible. For example, for this original graph, this will be a minimum spanning tree because sum of the weights of the edges is minimum in this case as compared to this spanning tree. A minimum spanning forest is a collection of minimum spanning trees. If you are given a non-connected graph like this, then every connected component of this graph will produce a minimum spanning tree. For example, this connected component will produce this minimum spanning tree, and this connected component will produce this minimum spanning tree. Collection of these two minimum spanning trees will be called as minimum spanning forest for this graph. Kruskals algorithm is a minimum spanning tree algorithm. If you are given an adjacency list like this, for example, vertex 0 is connected to 4 vertices. The edge between vertex 0 to 1 has a weight of 3. The edge between vertex 0 to 2 has a weight of 0. The edge between vertex 0 to 3 has a weight of 8, and so on. Using this adjacency list, you can produce a graph like this. In this example, a minimum spanning tree can be represented with these edges as the sum of the weights of these edges is minimum. In Kruskal's algorithm, we sort the edges with respect to their weights to get the sorted edges array. Note that every edge in a graph will have 2 entries in the adjacency list and it will have only 1 entry in the sorted edges array. For example, this edge has 2 entries in the adjacency list, this and this, and it has only 1 entry in the sorted edges array. Kruskal's algorithm uses union find or disjoint set data structure to produce minimum spanning tree. If you are unaware of what disjoint set or union find data structure is, then please refer to my previous video. I'll put the link in the description box. As Kruskal's algorithm depends on union find data structure, we'll maintain 2 more arrays. One array to maintain the parent of each subset and another array to maintain the rank of each parent. We'll initialize this parents array to make every vertex its own parent and will assign the rank of all the parents to 0. Now we'll iterate over this sorted edges array. For every edge, we'll see what are the vertices it connects to, and we'll do the union operation over the subsets for those vertices. The first edge connects to vertex 0 and 2. The parent of 0 is 0, the parent of 2 is 2. Since both their parents are different, we'll do the union operation over these vertices 0 and 2. While doing the union operation, we'll check what is the rank of both the parents. The rank of 0 is 0. The rank of 2 is also 0. Since both the ranks are same, it does not matter which vertex becomes a new parent. So let's make vertex 0 as the parent of vertex 2. And we'll also increment the rank of 0 to 1. Now, this edge is complete. We'll add a edge in our final answer. Now we'll move to the next edge. Vertex 1 has parent 1. Vertex 2 has parent 0. Since both the parents are different, we need to do the union of vertex 2 and vertex 1. We'll check what is the rank of parent of 2. It's 1. The rank of parent of 1 is 0. Since rank of 0 is more, we'll make 0 the new parent. Now this edge is also complete, and we'll add this edge into our final answer. Now we'll move to the third edge. This connects to vertex 0 and 1. We'll check what's the parent of 0. It's 0. We'll check what's the parent of 1. It's 0. So both of these vertices belong to same subset. Then we don't need to do anything here. We'll just skip this edge. Now we'll move to fourth edge. This connects to vertex 3 and 4. The parent of 3 is 3. Parent of 4 is 4. Both the parents are different, so we need to do the union operation. The rank of 3 is 0. The rank of 4 is also 0. So it does not matter which one becomes a new parent. Let's make 3 as the parent of vertex 4. Now, we'll also increment the rank of 3 in this case because both the parents had same rank before union. Now, we'll move to next stage. This edge connects to vertex 0 and 4. Parent of 0 is 0. Parent of 4 is 3. Rank of 0 is 1. Rank of 3 is also 1. So it does not matter which one becomes the new parent of the overall subset. So let's make vertex 0 as the new parent of 3. We'll also increment the rank of 0 in this case because the previous parents had the same rank. Now we are done with this edge also. And since we did the union operation, we'll add this edge to our final answer. Now we'll move to the next stage. This edge connects to vertex 0 and 3. We'll check what's the parent of 3. It's 0. The parent of 0 is 0. Both the parents are same. So we'll skip this edge. We'll move to the next stage. This edge connects vertex 4 to vertex 2. The parent of vertex 4 is 3. But the parent of vertex 3 is 0. So the overall parent of vertex 4 is 0 and the parent of vertex 2 is also 0. Since both the parents are same, we don't need to do anything here. We'll just skip this edge. Now we found the minimum spanning tree that we were looking for. Now let's look at the time and space complexity of the Kruskals algorithm. Initially, we were given the adjacency list, using which we created this sorted edges array. Sorted edges array is nothing but the edges are sorted with respect to their weights. So that will take a time of big O of E into log E, where E is the number of edges. Now, after that, we are also iterating over this sorted edges. So that will take another big O of E. For the union find data structure, the time complexity is big O of 1. That's almost constant time. So we can completely ignore that. See, overall time complexity of Kruskal's algorithm will be big O of E log E. Space complexity of the Kruskal's algorithm will be big O of V plus E, where V is the number of vertices. Big O of V will be required to maintain the parents and rank array, and big O of E will be required to maintain the sorted edges array. Now we'll look at the Java implementation of the Kruskal's algorithm. The first method that we'll look at is this get sorted edges method. This method accepts this adjacency list as an input and returns the sorted edges. This sorted edges array is sorted with respect to weights of these edges. In getSortedEdges method, we'll initialize an array list. Then we'll iterate over this graph for every source index. For example, here the source index is 0. We'll iterate through this graph. For source index 0, we'll iterate through all the edges. And then if edge of 0 is greater than our source index, which was 0, which is true in this case, then we'll add this trio to our sorted edges. For example, in this case, first trio will be 0, 1, and 3 because the weight is 3. The second trio will be source index 0, destination index 3, and the weight 8. Then we sort this sorted edges array with respect to their weights because we are storing weights in the second index, and then we are returning the sorted edges array. Now we'll discuss about this find parent method. I won't go too much in depth about this method because in my previous video about union find data structure, I have talked about find parent in depth. In short, if we have to find the parent of index 2, find parent method will give you the parent as 0, and it will also update the parent of 2 to 0. Now we'll talk about this union method. Just like the find method, I have discussed about this method also in my union find data structure video. What this method does is it checks what is the rank of both these parents, and whichever parent has the higher rank, it makes it the new parent. In case both the parent have the same rank, then it randomly assigns one of the parent as the new parent and it increases the rank of that particular parent. Now we'll talk about this get minimum spanning tree method. This method calls the get sorted edges method on our graph to get the sorted edges. Then it initializes the parents and ranks array. It also initializes this array list to store our minimum spanning tree. In this loop, we are making a vertex its own parent. Then we iterate through this sorted edges array. For every edge, we find the parent of the vertices this edge connects to. If these parents are not equal, then we do the union on these two vertices and then we add these edges to our final answer. In this loop, we are just converting our MST array list to this array format that we need as an output. If you like this video, then please hit the like button, share it with your friends, and subscribe to our channel.